Hi there, welcome to another video from Hegarty Maths. It's Mr. Hegarty here, our sixth video on advanced conditional probability. Let's start with some formulae I need you to know off by heart. For any events A and B, remember I told you the probability of A and B is the probability of A multiplied by the probability of B given A happened, or similarly probability of A and B is the probability of B multiplied by the probability of A given B happened. Rearranging each of these, we got the following equations. Now in the previous video I used any of these four at any time to solve some problems, so I need you to be able to learn those formulae and be able to use them at will. I did give you a quick way of remembering it. Probability of B given A, you always have on the top the probability of A and B. That's no matter what scenario, and when it's slash A it's divided by the probability of A, and when it's slash B it's divided by the probability of B. I tend to remember these two versions of it, and then I can rearrange to get the other two versions, but it's up to you how you remember them. And these were the type of questions we answered in the previous video, so double check you can answer those. That was just a case of remembering the formulae and applying them, and you should have got the following answers. Now we're going to be working out things like this, probability of A given B in the following, but just in a context question that uses tree diagrams, and it's usually the last part of such a question that just makes it a little bit more complicated. So let's start with a question we've actually already answered previously. Pause the video and double check you could draw the tree diagram in this conditional probability setting. Well, this is all about a cyclist and how his performance is affected by whether it rains or not. It tells us the probability that he crashes is 7/10 when it's raining, and it's 1/10 when it's dry. It gives us finally a piece of information on any given day the probability of rain is 1/3. So we set this up with a tree diagram. We thought to ourselves there are two things going on here. The first thing is whether it rains or not, and the second thing whether it crashes. And we put crashes second because it depends on whether it rains or not. So this is how we would have, and you should have, drawn the tree diagram. In the first instance, you think of the scenario where it rains or it doesn't rain. It rains with probability 1/3, so it doesn't rain with probability 1 subtract the third, which is 2/3, and that's your first branch. Then you would consider to yourself, well, let's imagine it did rain. We are told the probability he crashes when it rains is 7/10. So we consider the cases crash or not crash, and we carefully label our probability tree. This here is the probability he crashes given it rains. That is given in the question as 7/10. Therefore the probability he doesn't crash given it rains must be 1 subtract that is 3/10. So let's assume instead it didn't rain, i.e. it was dry, and let's go down this branch here. We're told in the question that the probability crashes when it's dry is 1/10. Therefore we can state the probability of crash given it didn't rain is 1/10 in that scenario, and finally the probability that he doesn't crash given it didn't rain must be 1 subtract 1/10, which is 9/10. And we've got our fully labelled tree diagram. Now that's all very well and good. We've done that type of thing before. What is different about these type of questions? Well, they would ask you the following parts here. What's the probability the cyclist crashes? What's the probability crashes given it's raining? What's the probability it was raining given the cyclist crashed? So you've got to be really good at these given statements and using our conditional probability formulae. Let's start off with B, which is something we've already done already. The probability he crashes, well, there are two scenarios in which he crashes. That is the probability that it rained and he crashed, and the probability that it didn't rain and he crashed, like that. We multiply the probabilities. 1/3 multiplied by 7/10 is going to be equal to 7/30, and in this case we do 2/3 multiplied by 1/10, which is 2/30. Adding them together we would get 9/30, which simplifies to 3/10, and we're done. What's the probability the cyclist crashes given it's raining? We're trying to work out the probability that the cyclist crashes given it's raining. Well, we don't have to apply any funny formula here if we think about it. That is actually a branch of our diagram. That is what that part of the diagram stands for, the probability of crash given it's raining, and that is just 7/10 reading off our tree diagram. But this is where we have to use these formulae. What's the probability it was raining given the cyclist crashed? I'm just going to go up here and do some working for this up here. We're trying to work out the probability it was raining given the cyclist actually crashed. Now that is not anywhere on our tree diagram. However, we know using our formulae that we mentioned at the start, this must be the probability of that it rained and he crashed divided by the probability that he crashed. Now we have both of these. The probability of rain and crash is 7/30ths. So I'm going to write 7/30ths, and we're dividing it by the probability he crashed, which we actually worked out in the part B, which is 3/10. So we're doing 7/30ths divided by 3/10, which is the same as 7/30ths multiplied by its reciprocal, 10/3. We could cancel that common factor of 10 here, and we would get ourselves the answer. 7 multiplied by 1 is 7, over 3 multiplied by 3 is 9. The answer therefore is 7/9, and we're done. So it's this last part, part D, that this video is all about. What about if the conditional probability is the other way around? And you have to use the formulae that I introduced at the start of the video for that. Right, let's do one more question and then we're done. Right, pause the video and have a go. So in this question we're talking about Sarah travelling to school by car, bicycle or on foot with probability of half, a sixth and a third, and then the probability of her being late using those particular means of transport. It asks us to draw a tree diagram and answer various questions. Let's start by doing the tree diagram on a separate page. Right, the first choice of our tree diagram is how Sarah travels to school, car, bicycle or foot. So we can just have 3 branches here. The probability of a car, we're told, is a half. The probability of a bicycle is a sixth, and the probability that she's on foot is a third, labelled like that. Subsequent to that, it talks about the probability of being late, and they're these probabilities. So doesn't matter what way Sarah goes to school, she's either late or she isn't. So for each of these there are 2 options. For the first one, what's the probability she's late given that she is using the car? Well, that's given to us, that's a fifth. Therefore the probability she's not late given she was on the car is 1 subtract that, which is 4/5. Next, let's assume she took a bicycle. Therefore we've got 2 things to consider. The probability she's late given she took a bicycle, which is given to us in the question as 2/5. Therefore the probability she's not late given she took a bicycle is 1 subtract that, which must be 3/5. Finally, let's consider that she went on foot to school. So the probability she's late given that she walked to school is a tenth, that's given in the question. So the probability she's not late must be 1 subtract that is 9/10. And that is our fully labelled tree diagram. Now we should be able to answer most questions, so let's keep flicking back to this tree diagram to help us answer the following. It says, find the probability that on a randomly chosen day Sarah travels by foot and is late. So we're looking that she goes by foot and she's late, so the probability of foot and late, well, we know to multiply along the tree, so we're going to do a third multiplied by a tenth, which is 1/30th. So we can go back to our question here and just simply write in 1/30th. Then what's the probability she is not late? Let's go to the tree diagram and consider the cases she's not late. It's in this case, in this case, and in this case. So we're going to have to work out each of these probabilities. The probability that she took a car and was not late, it's a half multiplied by 4/5, which is 4/10. For this is the probability she went on bike and she's not late, so the probability of bike and not late, which is going to be a sixth multiplied by 3/5, which is going to be 1/10. And this one here is the probability she went on foot and she wasn't late. Well, that's a third multiplied by 9/10, which is going to be equal to 3/10 if you multiply those out together. Now, so the probability therefore that she's not late is 4/10, add 1/10 is 5/10, add 3/10, which is going to be 8/10. So it's going to be equal to 8/10, which simplifies to 4/5, and we're done. Then it says, given Sarah is on foot, what is the probability she is late? Let's look at our tree diagram. Given she's on foot, what's the probability that she's late? Well, that's just reading off the tree diagram, isn't it? That's just the probability that she's late given she's on foot, which is a tenth. That was just something on our tree diagram that we can simply state. It's the last one that maybe we can't. Given Sarah is late, what is the probability she's on foot? We do not have the probability that she's on foot given that she is late. So we're going to have to use our formula for this. So let's just do some working up here. We're trying to work out the probability that she is on foot given she's late. So foot given that she's late. We know using our formula this is the probability that she's on foot and she's late divided by the probability that she's late. Now we should know both of these from our tree diagram. The probability that she's on foot and she's late, we've worked that out as 1/30th already. So that would be 1/30th divided by the probability that she is late, and we have worked out the probability she is not late. The probability she is not late is 4/5, so the probability that she's late is 1 subtract the probability that she's not late, which would be 1 subtract 4/5, which is 1/5. So we're going to do a 30th divided by a 5th, which is the same as a 30th multiplied by 5/1, which would give us 5/30ths, which simplifies to 1/6. So this final answer here, with all our working above, just quote our working, we would say it is 1/6, and we're done. And that's it for this particular video. Thanks loads for watching.